Hey, this is OXDF, and today we're doing the Advent of Code 2016, Day 22, Grid Computing, as part of the Revival of Code 2023. Let's take a look at the challenge. This write-up is a little bit confusing, but basically we have a bunch of devices on like a Linux machine that are like dev, grid, and then a node, x coordinate, y coordinate. And we're going to get the output of the df command, which is a real command like on Linux machines. That's going to be our puzzle input. You can instruct a node to move, not copy, all of its data to an adjacent node if the adjacent node has enough space to receive the data. And the sending node is left empty after the operation. Nodes are named by their position. We talked about that. Before we get started, basically, we're going to ignore position for part one, and we're just going to look across all the nodes. And for each node, we need to count them if node A is not empty, node B and A are not the same, and node A, it's used, is less than or equal to the avail on B. So that actually seems pretty easy. It's going to be a text parsing exercise. Let's go ahead and jump in. I will do my genday script for day 22 here. In the introductory video for this series, I show how this is made and what it does, but it gives us some stub Python to work with, as well as pulls this input for us. We can take a look. So this is, we have root at this grid center, df-h, and so we have all our nodes. Each one you get a size, a used, an available, and a used percentage. So let's parse this thing. We'll start by, I guess the first thing I'm going to do before I even create tests, I'm going to cheat a little bit. We're going to come in here and I'm going to create a device class, I guess, or a node class. We'll call it class node def underscore init. And we're just going to take in, let's just literally get this line right here. You can see what we're working with. Really what we want to do is for each node, we're going to have x, y, size, used, avail, percent. And so we can literally just do self.x equals x, self.y equals y, self.size equals size, self.used equals used, not user, used, self.avail equals avail, and self.per equals per. We can get rid of that now. Let's see, I think that's probably it for now. I guess the other thing we're going to do is we definitely need to compare nodes. And to me, the way we're going to compare nodes is just seeing if it's in the same position. So I'm going to just go ahead and define it under equal here. We're just going to take self and other. And it's going to return a bool. And we will return self.x, self.y equals other.x, other.y. I think that'll work. We might need to tuple this. Let's do that to be safe. Okay. So now we have our node. I'm not going to really bother testing this. We could if we want to be extremely detailed, but we're not going to. Next thing we need to do is parse all our thing into like a list of nodes. Now we want to test. So up here, let's see, we'll grab this. They don't give us any example data, but I'm going to create some. So we're just going to do a plus here. We'll call it example.text. And we will grab input.text and we'll grab like the first handful of rows here. And to make it a little bit interesting, we can see these are all, basically nothing fits anywhere here. So let's do a couple, like we'll switch this one, 20 and 69, means this is now 23% full. And maybe we'll do one, let's make one of them empty. Maybe one of those smaller ones. That doesn't matter actually. We'll make this used 0, available 88. Okay, sweet. So now we've got data. So we want to be able to test, let's see. We've got this. Let's come down here and we'll do def test parse. And we're going to pass in example. We're going to say nodes is equal to how are we going to do this? I guess we'll say aoc.parse example. So that's going to turn us a list of nodes, and now we can start to assert some things. So we can like assert len nodes is equal to, let's see, len example dot strip dot split lines. So I think like we should have a node for every line. We can assert that all is, let's see, so we're going to do d for, I keep saying d, n for n in nodes. And we can say we're going to assert that all of these is instance, comma, aoc.node. Make sure we have all of them are nodes. And we can do some like assert nodes sub 0 dot x is equal to 0. Assert node sub 3 dot size is equal to, on this, no, 0, 1, 2, 3, 92. Looks reasonable. I'm noticing actually an example, we're not going to get a node per line. We have 8 lines here, we only have 6 nodes, so we have to take off these top 2 lines. So let's do that up here, split lines, -2. Okay, so now I can run my tests. I'll do it through the debugger here. I've got a video that shows how to set this up if you haven't done it already. And I will run this, and sweet, none type has no len. So we're basically getting back none here, which is fine. Let's go and write the actual code. So to parse this, I'm gonna use regex. Seems like the easiest thing to use here. So here we're gonna say node re is equal to re.compile. And now what I really just want is I'm gonna grab, where's my example text? Let's just grab this, because we're just gonna basically use this line to make ourselves a regular expression. The device grid, this right here is going to be 1 or more digits. So this \d plus, and we're going to wrap it in parentheses to capture it. Same thing here, \d plus, so we capture that. Now we're going to have a bunch of white space. So I think that's \s plus for white space. Now here again, we're going to have \d plus, so 1 or more characters, \white plus, white space. Here we're going to have \d, but we want to capture. Every time I want to capture, I'm putting it in parentheses. And the plus just means 1 or more. And \d plus, and there we go. So we have this regex. So we compile that here. Now for parsing, we just need to do node re dot find all on puzzle input. And then what are we going to do? We'll do n for n in. So that's going to return a list. So now we can loop over that list. And for each one, we want to do node. And I think we can just do it like this. So that'll expand the found things out to pass them in as these. Now we're going to be passing in strings. So maybe we need to come down here and make these all ints. Actually, let's do it this way. They're all ints, right? So really what we want to do is, let's see if this works. Map int. So we're going to apply the int function to everything in n, then we're going to pass it into, so we probably need the map like this. Let's give this a try and see if this works. We need to return F5. Let's see if we error out here. No, we passed the test. Sweet. So this works. So basically what we're going to do is we're going to get, every time we find each time it finds this pattern, it's going to return me a tuple of 1, 2, 3, 4, 5, 6 values. That's n. I'm then going to take the map function and apply int to each of those n values. So all those go from strings to ints. Now I have a string, a list, or it's actually a generator of 6 ints. The star says expand that out and treat those as 6 individual items and pass those as 1, 2, 3, 4, 5, 6 into node. Create a node object. I'm going to return that. So that seems to be working nicely. Now, let's see. The test for, let's actually solve part 1. We don't need to parameterize any of this. We do want to pass in example. we're going to call aoc.parse on example and get back nodes. So we're going to pass part1 on nodes, and we expect to get back the number of devices that can write. So we better look at our example and say, so like 68 can go to this one and this one, so that's 2. 69 can go to these two as well, so that's 4. 68, that's 6. 73 can only go to the top, the 88, so that's up to 7. 20 can go to 8, 9, 10, 11, 12, and then nothing goes to this one. So I think our answer is 12. I'm not 100% sure on that, but we'll go with that for now. Part 1 here. Okay, we'll call this nodes. And so what are we going to do? We'll start with a count equals 0. And so we're going to say for a in nodes. We could prune right now if a is 0 and not do the second loop, but I'm just for readability, I'm going to do for b in nodes. There's also like some iter tools, like combinations we could probably just use fancily to get all the pairs. But this is just off the top of my head is what seems fastest. We don't have a speed problem here. So if a.used is greater than 0, we have 3 criteria, and a not equal b, and a.used is less than or equal to b.avail count plus equals 1. I think that might be it. We can return count. Let's give it a test and see how it goes. Oh, we're not passing something. Okay, 11 versus 12. That could be that we just counted poorly. Let's try this again. 68 does not fit in 22. No, no. 1, 2. 69, 3, 4. 68, we already know it's going to be 5, 6. 73, 7. 20. 8, 9, 10, 11, 12. Oh, but I counted myself. 11. Should be 11. Sweet. Where's my test? Let's make this 11. F5 again. We're passing the test. Looks like we got a solve here. Let's go over here. Change to current file. F5 this thing to run on the big input, and we get 1038. Sweet. Okay. I'm going to pause and read this, and I'll be back once I understand it. Okay. So in part 2, they actually give us some example data now. And the goal is to gain access to the data with the highest X. So if we have a grid, like in this example, they give us a 3x3 grid, the top right corner is what we want. And we start off, we need to get that into the top left corner. So basically what they give us, here's this picture of what they give us, where this node is 8 out of 10, this is 7 out of 9, this is 6 out of 10, here's 1, 0 out of 8. And they simplify this map, and this is interesting. They simplify it down to nodes are dots, except that they put parentheses around the starting node. The goal is G. They note this one is a very full node, which will draw as pound sign, hash mark, and it's not clear exactly why they do that, but I think that's there. And then also they have the exception, there's only one empty node in here, and it sits right here. And so the goal is to move G over here. So what you're going to do effectively is, you can see it here. They swap these two. So this one becomes empty and this one becomes full. They then can swap G into the empty one, moving the empty one here. Now they kind of move this one around. You can see all the way back until it's up in the start. And then they swap G, and now G's at the start, and they've won. And so the question is, what's the minimum number of steps? This seems like a really hard problem. What I'm thinking actually is we're going to take a look. Let's spend a minute and look at the data. I'm going to go up here, cat input.text into sort. Let's see, into head -3. Let's just take a look what we got here. Okay, so if we want to look at like sort minus n for number, k to pick a column, and we want to pick 1, 2, 3, 4. Let's look at what's available. Let's look at what's used. 1, 2, 3. Let's just do this into head. So we can take a look. So we are looking at the least used stuff. I guess maybe we want to grep out files. Maybe we want to do just a grep for grids that we. Cool. So now we don't get these root at, oh, we still do, oh, it's grid center. Maybe we do group for dev. Okay, so now we can see there's one node that has 0 usage, only one. So just like they said in the previous problem, there's only one node. And so then there's a bunch of nodes that use 64. So 64 is the smallest other than the one. If we go in reverse, put an R in there, there's a bunch of nodes that are like huge, that are using like 500 terabytes. Let's look at what's available. So that's column 4. So the biggest available is 89 in our empty node, and then after that it's 30. And so that's actually interesting. So our smallest data set is 64. Biggest available after the empty node is 30. So effectively what that means is we're only ever going to move into the empty node. We don't ever have to worry about trying to like combine two nodes or something. It's only going to move into the empty node. And that's important to note. I think it's going to be useful. Let's take a this. This might end up being a total rabbit hole. But def map, and we're getting totally away from test-driven development here, but we're just gonna, sometimes you got to do that. Draw map of nodes. And so what are we gonna do here? Let's figure out, so I'm gonna make like grid is equal to a dictionary. And I need to know the size of x, the max of x and y. So we can do like x max equal to max of n sub x for n in nodes. Better make this nodes. So we can loop over all of them and get the maximum x value. That'll work fine. Y max is equal to max n dot y for n in nodes. That looks good. And so now we can do for d n in nodes. If, so where's our map here? Let's look at the special cases. If the position is 0, 0, we want to, rather than make this thing take up so much space, I'm just going to give it a one character thing. So we'll say if n dot x equals 0 and n dot y equals 0, grid sub n dot x n dot y equals, we'll say like start. Elif, and let's see what the next one is. So the next one would be is our goal is going to be max x 0. So we'll do if n dot x equals x max and n dot y equals 0. Grid. That'll be easier actually. Watch this. We're going to do this kind of fun. We'll do at property def position self return self.x self.y. And so effectively what I've just done is I can now say node.pos and I'll get back a tuple of x and y. That'll make this a little bit easier. So we can say things like if n.position equals 0, 0. I just think that's so much easier to read. N.position equals, we're using a property because it's just built on other things that we're already storing, but this allows us again to just get that information. Okay, so now we can say, here we can do position. Like that. Okay, I only need a tuple there. Beautiful. Okay, n.position equals goal. So the other things, let's see, what else do they have in here? We need nodes, we need the empty space. So we say elif n dot used equals 0, grid n dot position equals underscore, like they did. The other thing they did was walls. And it's not quite clear to me why they're calling out walls, but like really full nodes, right? It's like a block thing. So we're never going to be able to move that data. So I guess if the data is bigger than the size of the empty node, but we don't know the size of the empty node, but we know the size of the empty node is roughly going to be, I guess it can never get bigger. No, it can get bigger. Let's go back and look at this data again. Down here, we want to sort on size of data again. Let's go into less. So the size of data, there's a bunch of 499s. The fact is, those are never going to move into the empty node. I think that's the real answer. So I think what we can say is, if used is greater than 100, I mean, because this, if used is greater than 100, we're just not even relevant to this problem. We'll say elif n dot size greater than 100, grid n dot position equals, else grid n dot position equals dot. Now we've got all of the, now we've basically effectively we've made this grid that we can use. So now we can say map string equals nothing for r in range y max, and we actually want y max plus 1 because we want to include y max, for column in range x max plus 1 map string plus equals, I guess we can just plus equals grid of column comma row. We do x comma y. We're doing it kind of backwards here, but okay, that should work. And then once we get through all the columns and we're about to increment the row, we'll do map string plus equals new line. And at the end here, we will print map string. And I'm doing this, I'm saving it all up and printing it once just to make, I think it'll make life a little bit easier if we need to actually return stuff. Okay, let's run this. F5. We've got an error. That close there. F5. Oops, let's see if we had an error there. Let's see what's going on. Console, what is n? Bunch of numbers. What's the error? Map takes one position. Well, it's not true. Map takes 2 arguments. Map int n. Oh, I can't call this map. Raw map. So I do this fairly regularly. Oh, we don't ever call this. So part 2, let's just put raw map data. Call this nodes. All right, we have a map. Okay, so in theory, we could write like some sort of BFS algorithm that would brute force every possible move, eventually moving G to S. That doesn't make any sense, right? What we really need to do, we can just count this, right? So we're going to need to move up spaces to reach the wall. We're going to need to move over till we reach the end of the wall. We're going to then need to move up here till we reach here. We're going to move all the way till we reach the second to last spot here. Once we're here, how do we move G? We swap with G, so then we move down, over, up, and we're in the same position. So to move G left 1 space takes 1, 2, 3, 4, 5, and we're back where we were. So 5 spots to move G over a space. So we can really just kind of count. We're going to kind of take a cheap solution here, but part 2, what do we need to know from this map step? We need to know where the, so we'll do return. What are we returning? We're going to return, we need to know the X max for sure. We need to know the position of the empty empty node, we need to know the position of the wall, of the space that we need to go around on the wall. What is that going to be? It's going to be leftmost wall. If we know that, we know position empty, we can calculate this distance all the way up, this distance over, and I think that might be it. So we need to create these things. So we'll say here, empty equals n dot position, and we'll say leftmost wall equals, I guess at this point we'll say we just need the x coordinates. So we'll say x max, and whenever we hit a wall, we can say leftmost wall equals min n dot position comma leftmost wall. So we're just going to keep updating that. So now we come here, we get draw map, and we'll get x max empty leftmost wall. That's really just the x of leftmost wall. So we do that. Now we can do that calculation we just set, right? So we'll say, I guess we'll say like moves equals 0. Now we can say moves plus equals, so the first move is going to be, do we return dot position? Okay, so we don't even want position, we just need, oh yeah, we do, okay. So we need, this is going to be empty sub 0, so the first empty, which is the x coordinate. We're going to need to move from here, that's going to be minus the leftmost wall, x, and we got to go one further because we don't want to get to the wall, we want to get to this next column here, right? So we'll do plus 1. And so we can say move left past wall. Now we say moves plus equals, and now we need to go from wherever we are up to all the way to row 0. So we can just say empty 1. That's the y coordinate of that. And this will be move to the top. Now we can do moves plus equals, and now we need to go from wherever we are, which is leftmost wall x minus 1. So we get to go from there all the way to the end, but not the second. So we need to go, we need x max minus 1, because we're trying to stop right before we get to data, minus leftmost wall x minus 1. Yeah. So in effect, that just becomes these minus 1s cancel out. So we have minus 1 minus minus 1. And we have that. Move to the goal data. Now we need to move the data. Each time we want to move the data one space to the left, it takes 5 spaces. We need to move it from x max to 1. So we'll do moves plus equals x max minus 1 times 5, because it takes 5 moves each time. And then once we are there, we'll have the state of where the empty 1 is at the start and data is right next to it, so we just need to add 1. Moves plus equals 1. Copy data into our disk. And this one will be move data next to disk. And the reason we can't just make this 6 is because that would move the data in, but then it would also pull this down, try to move it out of bounds. Like it does things we don't need to keep doing. So now we can return move. Let's see if we solved it. Oh, let's see. Sort of in tuple position 0. Oh, why do position 0 when you can do x? 252. Let's see if that gives us an answer. um, I'm tempted to kind of go back and write a generic algorithm that just takes an input and doesn't do the analysis to sort of figure out the walls. But man, did that seem hard. And we're already, what, 30 minutes into this, so I'm going to call it here. We got to solve, even if it involved, looking at it and kind of cheating. But I mean, that's part of the analysis, right? It's, can you understand the problem enough to figure out how to solve it? So I'm going to call it here. Thanks for hanging out with me today. Thanks for staying till the end. I'll talk to you next time. Bye.